Thank you for coming. I'm Joe Rickert from R Studio and the R Consortium. And what I want to do is try to give you at least one angle of a big picture look about what I think is going on in the R community. So when I first read this quote from John Chambers about, the very fabric of R being to connect to computational resources, and it resonated with me because it's the kind of thing I'm seeing, as I go out and talk to new people, trying to convert them to R or explain what R is. And when I had the opportunity to speak with John and, really understand about how it's exactly what they started out with in ancient times with S, the direct ancestor of the R language, and trying to get to good stuff. Fortran routines were the good stuff. And what I see now is that the R community of developers is continuing to do that in a big way. And what I'd like to do here is elaborate a little bit on that with the help of some examples. And at the same time, try to give you an idea of what I mean by connecting and what I mean by good stuff. So first off, starting at the top, there are other languages. Obviously, other languages have great strengths, so we want to connect to that. And I'm going to go quickly here and hope that we have some time to linger on some examples. The next thing is design-specific languages. So a DSL is an embedded kind of language that extends the capabilities of R in various ways. For instance, if you use the tidyverse, dplyr is a specific language for manipulating data. ggplot2 is a tiny language that's robust and describes how to do, how to build plots and visualizations. So there are other domain-specific languages. Of course, there's a whole idea of web technology and how R is embracing instead of fighting JavaScript-based applications. There's data sources. I mean, just getting data is good, and there's a lot of work that I see, and every month people are writing packages, that either provide APIs or putting data inside packages themselves. Of course, there's databases. This idea of data structures, the APACHE, this project here, the idea is to build language-independent data structures, which is another dimension of connectivity. So if you're sharing the same data structures, it's a very close relationship with the people who are thinking about other tasks, but you have something in common. And of course, there are these big platforms like Spark and TensorFlow. So let me start off with this is an interesting dynamic. So connecting with Python. The reticulate package is probably something that you won't use much as an end user, but it's providing tremendous leverage within the R world to go out there and connect with other resources, in particular things like TensorFlow. TensorFlow, written by Google, is the APIs to it were written in Python. So now we have a situation where R can go through the TensorFlow package to talk to the Python, to talk to TensorFlow. So what's happened here is this astounding thing, I think, where Python is now middleware for an R user. So you start there on reticulate, and you think to yourself, just in front of that somewhere, trying to access TensorFlow, and you're working in your R session, and what's happening is you're getting to Python, which is getting to TensorFlow, and from TensorFlow, you can either do deep learning models, which is what people normally think of, or you can go in other directions because, as I hope to elaborate on a little further, TensorFlow is a very robust platform for solving all kinds of statistical models. So Greta is an example of Bayesian, using TensorFlow to build Bayesian models. Down here, CVXR. CVX is a very powerful optimization set of routines. And CVXR is a DSL for describing optimization problems. And what you see I'm showing here is the CVXR developers used the reticulate package and TensorFlow to actually get access to commercial solvers available via Python but not available otherwise within R. So you have a situation where the dynamics are, it's like a web of interconnectivity where all kinds of things are coming together to make things happen. So Stan. Stan is a language for building Bayesian models. It's really big league, but it's even more than that. It is a language for expressing very powerful probabilistic relationships and building probabilistic models. What I'm showing here is a simple logistic regression, so it's not particularly Bayesian, but it's using the MCM, technique in order to solve for the parameters. I have examples in a repository with code behind it for several of these things. So if you have I'll put that up at the end. So I'm going quite quickly through here, but I encourage you to look at them because what I did was try to make them as introductory as possible and as easy to approach. The tidyverse, as I mentioned, is a DSL, or actually it's a ecosystem of DSLs. And what I think is really important about the tidyverse is it's extending the reach of R into other disciplines that normally you wouldn't think of as being accessible. You have people in computational humanities and social sciences and mathematicians who are doing abstract things and not modeling, starting to write R packages. I picked out one here, stematology, as an interesting package. I mean, the person who wrote this is a philologist, and he describes himself on his website. He's an academic and a scholar of ancient languages and medieval languages. So from the point of view of spreading the word about R, give me one person like this who's coming from a completely different field and finding value in the concept of, literacy and being able to write R scripts. That's worth 100 people just mindlessly typing Python scripts to move data around. So I'm really excited about this because it's an influx of new thinking and new people and extending the reach of R in other directions. Here's CVXR, as I explained. It's for optimization. One of the authors, Angie Fu, is going to give a talk at 10:30 tomorrow, and she'll go into some details. But I just want to mention here, this also expands the reach of R because what I'm showing here is their hello world example where thinking about running an ordinary least squares within R with LM and then formulating it as an optimization problem gives you the same answer. But optimization problems now allow you to tackle harder, different kinds of models that don't have closed form solutions that you wouldn't imagine within the context of just being confined either to LM or GLM. So it's a way of extending the reach of R by extending the kinds of ideas and tools. Nimble is anybody heard of Nimble here? It's been going on for a couple years, and you can see the acronym is hard to get your hands on. But it's basically a system for doing hierarchical Bayesian models that's also extensible to different kinds of abstract statistical formulations of stochastic modeling. And it's built on R. It uses the Bugs language as a way to formulate models. So it's a DSL that has a DSL within it because it uses bugs that describe the models. And it's built on two dichotomies that are really rich. One is that it separates the model from the algorithms. So you can formulate the language in bugs, and then there's a nimble modeling language to describe algorithms. So you can imagine you could have a model and switch out different kinds of things like gradient descent or something else underneath. Or you can build these models in the nimble language, these little module algorithms, and then use them as part of your repertoire when you build different models. The other thing is it separates the setup of the model from the execution, and it allows you to compile R code. So now you can generate compiled R code, which could be production level code, in almost any area. And again, I'm showing here a simple kind of model, but there's a more complicated one example in my repo. The web connectivity and JavaScript. I'm not going to say too much about this, except that, you know, R2D3, HTML widgets, of course, Shiny, these are things that have vastly expanded the reach and the look and feel of R. And it's making a big impact on why people come to R and how they use it. And the work continues. There's a package called rcrawler that I came across for web scraping. It looks like it's, you know, it's new and intense ideas. And then there's data itself, which should not be underestimated. Every month, I write a blog post on my top 40 packages and try to categorize them. And I see lots of people writing either APIs to data sources or actually putting data sets and making them available. So these are just a couple of posts that happened. One recently on World Cup data, and then this other thing on packages that I did last year, just picking out like the top 40 data packages from last year. And also I want to give a shout out to the R Open Side people. I mean, every month they write about 3 or 4 packages that are APIs to scientific data, and there's something you should really pay attention to, the like unglamorous in a way, but steady and solid work that they're doing all the time to make data within reach. Database connectivity. So you saw DBI up on the previous slide there. So it's an R package that provides a common set of interfaces, and it's making it really easy for people to write back ends that are, you know, rationalized. So you use basically the same set of code. You can get the different databases. And I think it's so important that the R Consortium has funded this kind of work on a continuous basis, because it's something that we need to keep up with. So it's continuous improvement. And I see that kind of thing in the R community. People, you know, tremendous commitment, not just to do something good, but to continue to make it available. And then there's this idea of pushing down the analysis that you can do with dplyr and dbplyr into the data set, you know, the data itself. So now it's getting easier than ever to extend, to connect to the good stuff, to get to the reach inside SQL databases and pull them out. And then I mentioned the URSA Labs project, where what you have is the idea of a data, you know, language-independent data structure, something in a columnar store that will be available to language, you know, to all different kinds of languages to analyze. It's a tremendously, you know, ecumenical idea that I think will kind of flatten you know, it'll dampen the language wars and give people the opportunity to see what can be achieved by cooperation. So I'm really looking forward to that. And then there's these big league platforms. Of course, there's sparlkyr, which enables you to sit at your console and you know, and get access to data on a Spark cluster. You can run Spark's MLlib from it. You can use the same technology to connect to a Databricks facility. So it's the kind of thing that helps you put R in production, or at least integrate R into production environments. And then there's the TensorFlow platform. And this, I think, is really exciting because TensorFlow is not just deep learning, right? TensorFlow, some genius computer scientists got together and decided, you know, where would we start from first principles to build something that can run on any hardware in a distributed fashion and work quickly. So being computer scientists, they knew about data flow languages, they implemented that. It's mostly implemented in, again, with Python, but with the work that's been done through Reticulate and building R packages, we as R users now have full access to any of this, I mean to all of this. So you see here the basic idea of the TensorFlow itself is that tensors, which are just multi-dimensional arrays, they flow around through directed graphs. The graphs have elementary kinds of operations. If you read the papers on it, it turns out that the graphs aren't even deterministic. They have probabilistic components to them, and yet they come up with the right answer. So the applications here are deep learning, Bayesian modeling, and more. You can build theoretically any kind of mathematical or statistical model in TensorFlow, design it in R, and then have it run on a big league distributed environment. Deep learning, there's been a lot of talk about that, so just a slide on this is that the idea is that it works with thinking of data as moving from one representation of the data to another until you get something that's useful. It learns by iteratively working through many representations of the data. They can be fragile, but deep learning models are doing superbly in computer vision applications and text processing. And we have a number of packages that give you windows into how to use TensorFlow. So the Keras package is something that you would use if you wanted to get the easiest route into doing deep learning models with R. And then you have different levels of access to the TensorFlow graph. You can work with predefined models, say as in TF estimators, or you can actually go to very low-level API to work with the data flow graph itself. There's lots of choices there. And then this idea of the Bayesian modeling. So the idea here is to use, since TensorFlow is a completely generalized platform, it doesn't have to be stuck with just deep learning. The people in the Greta project said, hey, let's build an MC sampler right on the TensorFlow. And so you can write Bayesian models. Here's an example of doing something, just a very simple model. And you can see that the diamonds over there represent edges. That's the flow graph that's generated by the model. And what you have is a normal distribution and have parameters feeding into it. The SD is a student's t-distribution. And when you work with these things, you end up with very complicated graphs. But I have an example of a model that you can start with in the repo. And that's about it. So what I wanted to do was to consider this idea of R being a place where the dynamic of the community is to reach out and make accessible all kinds of interesting computational resources to involve lots of people. And here you have some resources for following up on what I've done here. And thank you.